Welcome to Lecture 12. Last lecture we discussed and introduced concepts related to decay. That includes half-life, which is closely related to what's known as the decay constant. These metrics are what help us understand how to model the inventory of different isotopes that might be present in a sample. It also helps us quantify the activity, which is defined as the decays per second in units of Becquerel, or we can convert that to units of Curie. So with those metrics, we can quantify all these parameters that are of interest to us in the sample. Today's lecture, we're going to go into more detail on a lot of those concepts. We're going to look at decay chains that are closed, meaning that I start with some radioactive isotope and it decays until it reaches a stable isotope. So that's an example of a closed system, a closed decay chain. We'll first explore those, and then we will, towards the end of the lecture, then we will venture into the modeling approach that one would take when we have sources and sinks for each of the isotopes. These sources and sinks can include things that are not related to the decay process, such as fission that is going to produce a certain type of isotope, or there's a potential statistical potential of producing a certain isotope. It could include ingestion of certain isotopes. Sinks might include the biological removal rate of said isotopes. And so we're extending the analysis at the end of this lecture to include any other sources and sinks that could be producing or removing any given isotope in that decay chain. So we'll start by looking at more simple cases. So we'll recall the inventory expressions that we developed last lecture for a single decay process where we're going from a radioisotope, unstable parent, down to a daughter product that happens to be stable. And so in this case, this on the left-hand side here, this is the rate at which the parent isotope that parent isotope is changing, the dN dt. And the fact that there's a negative sign on the right-hand side means that the inventory of this unstable parent is decreasing with time. And the question is, we have the daughter now, N2, the inventory for N2, that will also be changing with time, and we will assume that at the beginning, at time equals 0, that this inventory was also 0. So at time equals 0, we had nothing but N1, and as time goes on, every one of those atoms is going to change, is going to decay into isotope number 2. And so just as we had a negative rate with the isotope, with the radioisotope, isotope number 1, we're going to have a positive rate of change for the inventory of the second isotope, which is stable. And the rate at which that happens, this dN2 dt, this is going to be equal to the same, whatever I am losing from the inventory of radioisotope 1 is the same that I'm gaining in the inventory for isotope number 2, which happens again to be stable. And so this is going to simply be lambda 1 N1. So any parent decrease is going to result in a daughter increase. That's what this is saying. So I take this same expression that was a sink in my first rate balance, and I'm going to dump it in as a source in my second. So I lose it from the first isotope, gain it in the second isotope. And so this first expression for isotope number 1, we've solved this a few times now. So N1 of T is going to be some initial atom count for that isotope, and that's going to then decay in an exponential manner according to the decay constant. So that is my expression for N1. My goal here is to find N1 and find N2. And now we can take that second expression and this is lambda 1 N1 of T, and we're going to take this N1 of T and substitute it in right there. So then this will be N, the initial number of atoms for my radioisotope. So now I have this expression where I've got the time rate of change of N2 equals this. And everything in front of that exponential is a constant, lambda is a constant, and so I can just simply integrate this. And I evaluate it at the bounds, and I can get from 0, well actually technically it would be, as we integrate this, technically this would be, we'll just scoot it down here. And then we'll integrate the right hand side. And we're going to integrate from time equals 0 to some time t. Technically to be proper, we would put some other variable here, call it s or t prime. So we're going to evaluate this, we're going to integrate it from 0 to t, and over here we're going to integrate this from n2 naught up to some n2 of that time t. Now n2 naught is 0, and so now we can just evaluate that from 0 to some n2. So we get n2 t on the left hand side, and on the right hand side everything in here is a constant, so this just still becomes n1 0 lambda 1 times, and then we're going to integrate this, negative 1 over lambda 1 times the exponential of negative lambda 1 t. That is the integral of my exponential of minus lambda 1 t, and then I evaluate that from 0 to t. And so I've got my initial inventory of my parent of the radionuclide multiplied by its decay constant, lambda 1, and this will then be negative 1 over lambda 1. Actually, we can just, what we'll do is we'll just cancel those out. And so we've got negative exponential of negative lambda 1t plus exponential of 0 is 1. And so n2 of t then just simply equals and this is not surprising, this is exactly what it equals, because we know that whatever I lose from the parent is what is gained in the daughter, and therefore all I have to do is take what I start with in terms of the parent and subtract to get my n2. It's just going to be whatever that happens to be, whatever my parent population happens to be, my parent inventory happens to be, and if I take the original amount and subtract that. So whatever's left over from that has to be my daughter. So I've got two expressions now, and this is just a sort of a review. We went through it in a more formal way just now compared to last lecture, but this is the process one would follow in order to eventually develop expressions for inventory of all the radioisotopes in the entire chain. So we see a more complicated chain down here. The example we went through was the most simple example you could find for a decay process. You got one radioisotope, unstable and decays down to a stable daughter. But here we've got 11 different decay processes. We've got 11 different half-lives at 11 different decay constants. And so the question is, well, what do we do with this? And what we'll do to make some insight in here, we'll pick a group of 3, maybe the last 3 or any 3. This is, although this says stable, there are different scenarios where we can approximate that as being stable. But this is a more simplified case where we've got 2 daughter decay process, and we've got 2 lambdas, and eventually we reach that third x3, which then becomes stable. And so just like we had before, this is my decay constant. My decay constant from going from isotope 1 to isotope 2. And this here is my decay constant going from 2 to 3. And so I'm going to start out just like I did before. I've got the time rate of change of isotope 1, and I ask myself, okay, what is that? Where is that going? And it's decaying down to isotope number 2, so this is just the same as it was before. Nothing's different there. And now let's look at our second one. I have what is being gained from the parent, lambda 1 and 1. I lose it from the parent, gain it to the daughter, but this also decays, and that's going to be related to N2. And then my third one, which is a stable one, is just going to be whatever is being lost from isotope number 2, that is what's being gained from isotope to isotope number 3. So this is just lambda 2 N2. And so for isotope number 2, we have a source and a sink. So this here is the source. If I live in isotope 2 environment, then there are isotopes being generated for that N2. There's atoms being generated for N2 through the decay process. That's a source. But I'm also losing atoms through another decay process to isotope number 3. So this here is my sink. And when the rate equations are expressed like this, then typically that's how you're going to know sources from sinks, just by looking at the signs of the terms in these expressions on the right hand side. A positive term will be a source, a negative term will be a sink. And we are restricting ourselves at this stage to looking at just the decay processes. But again, at the end of the lecture, we will extend that to be more generic and look at other types of sources and other types of sinks. So what we have here is a set of 3 differential equations in terms of N1, N2, and N3. They are ordinary, they are differential, so ODEs. Because there's 3 of them, we have 3 conditions that we need to specify. Because this is a time rate of change, those are typically going to be some sort of initial condition. So knowing how many of atoms we have of isotope 1 and how many atoms we have of isotope 2 and 3 at time equals 0, for example, is an initial condition that is generally going to be specified there. So the question is, do we start at time equals 0, do we start with a sample, a pure sample of where all the atoms are of isotope 1, or do we start off with some mixture of 1, 2, and 3? And technically, from a mathematical perspective, it doesn't have to be an evaluation at time equals 0. It doesn't have to be a quote-unquote initial condition, but we do need to specify 3 values at some time. And it's just most convenient and most typical in a set of ODEs like this to specify the initial conditions. So we need our initial conditions. And that will look something like this. N1 of 0 equals whatever my initial inventory is, and we will assume in many of these cases that we have at time equals 0, we have a sample that is purely isotope number 1. And so the N2 of 0 equals N3 of 0 equals 0. I don't have any atoms in this sample of isotope 2 or 3. So looking at this first differential equation up here, these are our 3. And there's nothing new, just as a reminder, there's nothing new about that expression for isotope number 1. It's just a simple decay process going from isotope 1 to some daughter product. And so our solution for N1 is no different than it was before. Since we know the initial inventory, then that will decay in an exponential manner, and the decay constant is the number that helps us determine that. So now let's go to N2. In order to evaluate this, we've got to look at the differential equation, which is going to be equal to lambda 1 times N1. We just determined what N was, so we'll substitute that in here. So that's the first term. That's the source, and then we just have minus lambda 2 N2, which is a function of time. So how do we solve this? We are going to use an integration factor, and what that means for anyone that is rusty on this is that we are simply going to multiply each and every term by some exponential. And in this case, we're going to choose lambda 2, exponential of lambda 2 times t. So if we multiply every single expression, or every single term, with this expression, so now we have this, times lambda 2t equals lambda 1 multiply that by our integration factor, and then we have our final term, and we multiply that as well by the integration factor. And the power of this comes into play by combining these terms together. In particular, we're going to combine this term and this term. So we're going to move this term over to the other side. And so what we've got is dn2 dt exponential of lambda 2t plus lambda 2 n2 times exponential of lambda 2t. So that's now my left-hand side. My right-hand side, I'm going to keep the same. I'll keep the rest of the terms there. The rest of the terms, I mean the only other term. But these two terms on the left-hand side here, I can combine them and express them as the derivative, the time derivative, so ddt of the product of two functions, one of them being n2 of t, and the other one being that integration factor. So if I had two functions in there that are both time dependent and I take the derivative of them, I need to apply the product rule, which gives me these two terms that are shown here. And so then this just equals lambda 1 n1 naught exponential of lambda 2 minus lambda 1. Taking those exponents and combining them together. So now we can separate and integrate, just like we did last time. And this process that we're following here is going to be the same regardless of how long the isotope chain is, or the decay chain is. Start with the easiest one, start with the original parent, and then just work your way through each isotope. And we're going to look at different shortcuts for this as well. So separate and integrate. I'm going to integrate this expression here is just d of n2 of t exponential lambda 2t. And here I'm going to bring the lambda 1 out, the initial inventory of isotope 1 out, and then I'm going to integrate the exponential of lambda 2 minus lambda 1 t. And I have the dt over there. This, of course, is going to go from 0 to 2t. And what's going on the left-hand side is I have this d of two functions, and so I have to evaluate them at time equals 0 and at time equals t. And so this will be n2 of 0 times the exponential of lambda 2 times 0, so that's times 1. But as we recall, the initial inventory, so that n2 at time equals 0 is going to be 0. And then up here, this just becomes n2 of t times exponential of lambda 2t. So the bottom bound of that integral on the left-hand side is also 0. But it's only because that initial inventory of isotope number 2 is assumed to be 0. And if it were not, then we'd have to be careful what we choose for the bounds here for the integration. So then the left-hand side just becomes n2 exponential of lambda 2t. The right-hand side is going to be lambda 2 minus lambda 1 times the exponential of lambda 2 minus lambda 1 t, and then we integrate that from 0 to t. And once we do that, we find that we have the exponential of lambda 2 minus lambda 1 t, and then we evaluate it at 0, so we get minus 1. So now we're going to take this and divide both sides, and so we're left with the expression on the left hand side of just n2 of t. And if I do that over here, I'm going to distribute it through these brackets. Well, let's just write this down first. So now I've got two terms. I've got the exponential of lambda 2 minus lambda 1 multiplied by t, and if I divide that by exponential of lambda 2t, that's the same thing as multiplying by exponential of negative lambda 2t. And so this one washes away, and I'm left with exponential of negative lambda 1t minus the exponential of negative lambda 2t. So this now is my expression for inventory of isotope number 2. Now we march down and we go to isotope number 3. For n3, then we've got dn3 dt. In this case, we didn't have any sink. It's just, this is the stable daughter, and so I got nothing here but a positive lambda 2 n2. And I have an expression for n2, which is up here. And so this just becomes lambda 1, lambda 2 over lambda 2 minus lambda 1 minus lambda 2t. And I can separate and integrate that. So this then just becomes the integral of dn3 from n3 naught up to n3 of t. And initial inventory, again, right there is going to be 0. And on the right hand side, I'll bring all this out to minus lambda 1. Initial inventory of the first isotope. And you see this N1 naught, so my initial count of atoms that are all isotope number 1, this is going to get carried through each of these. And then I want to just integrate this from 0 to t, exponential of minus lambda 1t. So after I integrate that, then I'm left with n3 of t on the left-hand side. And I've got this one still out in front, lambda 1, lambda 2. And for the first term, I've got negative 1 over lambda 1 exponential negative lambda 1t. And I'm going to have minus a 1 over lambda 2 exponential negative lambda 2t. And this we will evaluate from 0 to t. And we're going to reverse the order here, so I've got 1 over lambda 2 times exponential lambda minus, or negative lambda 2 times t minus 1 over lambda exponential negative lambda 1t. That's me evaluating it at the upper bound. And now I've got to subtract the one from the lower bound, which ends up being exponential of 0 is a positive one here. And when I substitute the 0 in here, I get a positive one. And then when I substitute the 0 in here, I get a positive one, but then I've got the negative 1 is not negative 1. I got to multiply it by 1 over lambda 2 and negative 1 over lambda 1. And so this ends up being plus, now I've got to subtract the lower bound. So then the signs change, so I got 1 over lambda 2 plus 1 over lambda 1. So that is my expression for N3, the inventory of isotope number 3. And I can manipulate this a little bit more to clean it up. These two terms are going to be the same thing as plus lambda 2 minus lambda 1 over lambda 1 lambda 2. And you can see that that's what we have out here. And so if I carry that through, then I'm left with the following expression for N3. So I've got N1, 0, and 1 naught. So that's my initial inventory of isotope number 1. And I've got lambda 1 over lambda 2 minus lambda 1 minus lambda 2 over lambda 2 minus lambda 1 times this exponential. And then I've got plus 1. So what do I have at time equal to 0? I've got lambda 1 I've got lambda 1 over lambda 2 minus lambda 1 minus lambda 2 over lambda 2 minus lambda 1 plus 1. Well, these two things combine to be negative 1. So negative 1 plus 1 is 0. And that's what we expect for the inventory of isotope number 3 at time equals 0 was 0. That was our initial condition that we specified. So then here's the three expressions. I've got an expression for N3. I've got an expression for N2. And then my expression for N1 is right here. And then if I need to find the activity, I can just multiply each of these by their respective lambda values. So the activity for the stable product is obviously 0 because I'm not changing those atoms. But I'll have an activity for isotope 1 and an activity for isotope 2. But I'll have inventories for all three. Let's go to a couple examples here. In example 12.1, we are starting with the, let's see, a decay chain. The similar scenario as what we just analyzed. And we've got lambda 1 equal to 0.1 inverse second. And we want to analyze and develop approximations for the following cases. So we've got the scenario where lambda 2 is greater than lambda 1, and then the scenario in part B where lambda 2 is much greater than lambda 1, 50 times what lambda 1 is. So we'll explore this analytically first, and then we'll go to some software to run the simulations of this and plot the results, that sort of thing. So we already have, and we want to plot the activity. Right, so the activity of 1 is just going to be the inventory multiplied by the by lambda 1. And so this is going to be n, just taking our expressions what we had before, so n1 naught times lambda 1 times the exponential of minus lambda 1t. And this a lot of times is going to be called the initial activity. And so this also decreases in an exponential fashion, just like the inventory does. So for isotope number 2, that activity is just going to be N2 times lambda 2. And this will be taking our expression that we just developed from our notes. We've got N1 naught multiplied by lambda 1 lambda 2 over lambda 2 minus lambda 1 multiplied by the exponential of minus lambda 1t minus exponential of minus lambda 2t. So we've got two different exponential terms in there, and this, if we combine these two terms here, this also equals that initial activity for isotope number 1. And so what we're going to do is we're going to normalize these plots. When we plot the activity, we'll normalize them by that initial activity of isotope number 1. And so this then just becomes that initial activity multiplied by lambda 2 over lambda 2 minus lambda 1 times these exponential terms. So as we have, let's look at these cases now. For case A, as we have lambda 2 equal to 2 lambda 1, then what's going to happen is that the activity, none of this affects the activity of isotope number 1, but it does affect the activity of isotope number 2. And that's because if we look at these terms here, I've got an exponential decay here and an exponential decay here. As time increases away from the initial time equal t equals 0 value, then you're going to have both of these decaying, but if one is larger than the other, it's going to decay a lot faster. And so that term is going to essentially drop out once you get past a certain time. And so what we have here for a normalized activity, so A2 divided by that initial activity of isotope number 1, this will just equal lambda 2 over lambda 2 minus lambda 1 times exponential of negative lambda 1t minus exponential of negative lambda 2t. But this term here, since lambda 2 is larger than lambda 1, this is going to decay faster. And so what ends up happening is that term can be neglected. And so we could say that this normalized activity then is going to approximately be equal to the following. So what does that mean? That means that the activity of 2 and the activity of 1 are going to be related to each other. Because this here, if I move the initial activity of isotope number 1 back to the other side for a minute, then we've got lambda 2 minus lambda 1 multiplied by that initial activity exponential minus lambda 1t. So this here was exactly what I had for the activity for isotope number 1. And so the two can be related to each other with the following. The activity at 2 can be approximated as the activity at 1 multiplied by some constant. In this case, the ratio of my decay constant of lambda 2 divided by the difference in the decay constants. And so this here is termed transient equilibrium, which is a confusing label. It's transient because things are changing with time, but it's equilibrium in the sense that if one knows the activity for isotope 1, then you can simply multiply by this factor here, this lambda 2 divided by lambda 2 minus lambda 1. This should be a 1 there, sorry. Lambda 2 minus lambda 1. And then we know what activity at 2 would be. So this is called transient equilibrium, and this is going to occur when lambda 2 is greater than lambda 1. Now for part B, we have lambda 2 equal to 50 times lambda 1. And so we've already established the fact that we have transient equilibrium because lambda 2 still is greater than lambda 1. But if we look at the constant that we're multiplying out in front between the two activities, then in this case, with this factor of 50, what we would have there is 50 divided by 49. And at some point, we can just approximate that as 1. And so we'd say this equals 50 over 49. And we can say, you know what, that's approximately equal to 1. The bigger that difference becomes, then the closer that is to 1. And so if I'm off by a few orders of magnitude, I've got 2,000 over 1,999. And we're at some point, we should be comfortable just calling that 1. And so in this case, if I have lambda 2 much greater than lambda 1, then my activities are going to be approximately equal to each other. And this is called secular equilibrium. And that's going to occur when lambda 2 is much greater than lambda 1. These are two conditions that we'll explore with some software here in just a minute. But let's talk on as kind of a side note, not related to this particular problem, because in this problem both A and B have lambda 2 greater than lambda 1. But if I have lambda 2 less than lambda 1 or lambda 2 much less than lambda 1, I can come up with similar expressions. They are going to look really similar, but just swapping out lambda 1s and lambda 2s. And so let's hurry and write those down just as a side note here. So if lambda 2 is less than lambda 1, then my activity at 1 is going to be the same, but my activity at 2 is going to be approximately equal to, instead of lambda 2 or lambda 1 in the top in the numerator, so if lambda 2 is less than lambda 1, then we'll find that the activity for isotope number 2, normalized by that same initial activity of isotope number 1, then this is going to be approximately equal to lambda 2 over lambda 1 minus lambda 2 times the exponential of minus lambda 2t. And so you can see that we've changed the order of this. That comes from the fact that instead of the second term decaying faster, it was the first term decaying faster, and this negative here was distributed out there to become lambda 1 minus lambda 2. But the point is we have a different exponential term because the other one now decays away much faster. And if we have lambda 2 much less than lambda 1, we can simplify that term out in front of this expression we just listed here, and that just becomes lambda 2 over lambda 1. The ratio of those two. So in other words, if we take this A1 naught and move it back over, then we see that the activity for isotope 2 is going to be approximately equal to that A1 naught was N1 naught times lambda 1. That was what A1 naught was. We'll multiply that by lambda 2 over lambda 1 times the exponential of negative lambda 2t. These cancel out, and we can see that this is approximately equal to N1 naught times lambda 2 exponential of negative 2, lambda 2t. And so in other words, what's happening here is that if lambda 2 is much less than lambda 1, that means that my half-life is much larger for isotope 2 than it is for 1. And so I decay much quicker from isotope 1 to isotope 2, and it just kind of gets built up there. And so what's happening for the activity for isotope 2, the expression for isotope 2 there, it's as if I have the entire the nuclei available to me. It behaves as if I'm starting with this isotope number 2. And so that's and it makes sense from a mathematical standpoint, and then hopefully it makes sense from a logical standpoint, just to think about if I have a much longer half-life for isotope number 2, then all those parents from isotope 1 are decaying down, and then they're just kind of building up, and I probably don't, depending on how big that difference is, I might not have all of those available to me, but if I had anything a few orders of magnitude different, then it's going to behave as if, again, all those atoms are isotope number 2. So let's go to MATLAB here. And so we'll start with this expression given in the problem statement. We have lambda 1 is 0.1. We have lambda 2 equal to 2 times that. This time vector will just go arbitrarily for now to 50 seconds. And then we want to look at the norm, so the normalized values for the activity of 1 and activity of 2. And this is my expression for activity 1. It's going to be the exponential of negative lambda 1 times my time. And I'm stepping through time here from 0 to 50. And for my normalized activity for 2, this will just be lambda 2 divided by the difference between them, lambda 2 minus lambda 1, multiplied by those two exponential terms. I got exponential of minus lambda 1t, exponential of minus lambda 2t. And if I want to look at the inventory, I'm going to normalize that by the, it's not given to us in this problem statement, but if I normalize by the n1 naught in these cases, then I'll get my normalized value for my inventory of isotope 1, and that's just exponential minus lambda 1t, and my inventory for state, or for isotope number 2, then the expression given here, lambda 1 divided by that difference in lambdas, and then I've got the two exponential terms just like I do for the activity. So, and then we just plot the results, looking at time as on the x-axis, and then the activities for isotope 1 and isotope 2, labeling the axes, etc. And then for figure 2, we look at the inventory. So this is the inventory, and this one is the activity. So going back to our expressions, in this first case, we were expecting transient equilibrium, and it's not, and that was in terms of activity, and that it's not readily apparent that that's the case here. We can see as we decrease the number of isotope 1, we're increasing the number of isotope 2, but then at some point I start to decay away from isotope number 2 into the final stable daughter of isotope number 3. And so I build up the inventory, and then it dies down after some time window there, maybe 7 seconds or so. But I can see I can more easily visualize the secular equilibrium if I, instead of just the plot here, which is just going to be a standard xy, I do a log on the y-axis and a linear on the x-axis. Do the same thing down here. And if I rerun these, you can see that this, for isotope number 2, that's the activity. This is the activity for isotope number 1, and they are on a log y-axis plot. These two are parallel, and they're offset by a value of lambda 2 over lambda 2 minus lambda 1, just as we saw. And so if you plot this on a log scale, at least on the y-axis log scale, you will be able to most easily identify secular equilibrium when it occurs, because that's what it looks like. You have that activity, they look parallel to each other on a log plot. So now for part B, all I need to do is change this 2 to a 50, and you can see that my The lines here come closer together. At some point, again, 50 divided by 49, is that close enough to 1? Or do we need to get larger than that? Who knows? But let me change the time window here to get a better view of it. And so the ratio of these two is approaching 1, and if that number 50 were to increase to something even larger, then we'd get something even closer. And so this is what's known as secular equilibrium. And again, it's most easily observed when plotting on a log plot for the y-axis. And it's a little bit easier to see even on compared to the transient equilibrium, it's easier to see when secular equilibrium occurs even on the linear plot, but it's most easily recognizable. Both of them will be on a log plot. You can see in this case where we have the count, then because the activity of isotope number 2 is not the activity, but the activity is high, but the decay constant is so much higher, 50 times higher than that of 1. What's happening is I decay from isotope 1 to isotope 2, and immediately as soon as it's available, it's in a comparative sense to how long it takes for something to show up from isotope 1 to isotope 2 bin, then a much quicker rate get rid of it to isotope number 3. So the activities become constant. As soon as one's available, that's about when I'm getting rid of it. And so the decays per second is going to be consistent and nearly identical for both isotope 1 and isotope 2. So let's go back to a second example now. In example 12.2, the decay scheme from plutonium to neptunium to uranium. So I've got some beta decays here going from isotope number 1 to isotope number 2 to isotope number 3. So initially I've got 0.5 micrograms. So that's my initial mass. From that I can figure out what my initial inventory is. And I have no initial inventory of either of the two daughters. So we want to find the time when the activity of isotope number 2 in this case is at a maximum. And so we saw on the previous plots that the activity for isotope number 2 starts at 0 and builds up and then decays down. And so we want to find out what that maximum point is. And then we want to, when we find that time, we want to substitute that into the inventory expression for U-233 to see what the population looks like there, what the inventory is. Once we find the number of atoms, then we can find the mass. So we have isotope number 1. We've got to find its decay constant. We've got to find the decay constant for isotope number 3, or for 2. And technically, uranium-233 is not going to be stable either, but if it's many orders of magnitude, if the half-life is many orders of magnitude larger, then I can call it quote-unquote stable. So let's go look at these isotopes. We'll start with plutonium-233. And so I've got my half-life here of 20.9 minutes, and that's going to be a beta decay to neptunium-233, and that's got a half-life of 36.2 minutes, and that's going to be another beta decay or electron capture down to uranium-233. Now this one has a half-life of 1.59 e to the 5th years, And so that compared to my half-lives of the previous ones, 36 minutes, 36.2 minutes, and 20.9 minutes. This is many orders of magnitude larger than either of these two. And so I can treat this one depending on the time scales I'm looking at it, but I for intents and purposes of this problem, I can treat that as a quote-unquote stable. And so not my lambdas, my half-lives. My half-lives for isotope number 1 was 20.9 minutes. My half-life for isotope number 2 was 36.2. And then isotope number 3 had a half-life of 1.5919 times 10 to the 5th years. So 160,000 years. So we're going to call that stable compared to tens of minutes. We'll call that stable. So we need to find the initial inventory of isotope number 1. And we do that by looking up the molar mass, the AMU value. So this will be equal to the mass, the initial mass, which is given in the problem statement. We'll have Avogadro's number, and then we'll divide by the molar mass of that first isotope, keeping in mind that the molar mass of isotope 1, so this is plutonium-233, AMU per atom is equal to grams per mole. So if I look up the AMU value for plutonium-233, I'll eventually find out that the initial number of atoms of that first isotope is going to be 2.584 times 10 to the 22. And that will be at time equal to 0. And so what we're expecting here for, we'll call this a J of t over a 1 naught. What we're expecting is that the activity for isotope number 1 is going to start out at the highest and do that sort of thing. This is going to decay with an exponential manner. And then we'll have isotope 2 is going to build up, and then it's going to start to decay, something like this. And we're looking for this point right here where my derivative is going to be equal to 0. That's what we're looking for in part A, is to find out at what time does this occur, when the activity of isotope number 2 is at its maximum. So in order to find that point then, in part A, we're looking for that point. In order to find that point, we've got to look at the expression for activity. We can force that to be equal to 0. That's going to be d dt. The activity of 2 is going to be lambda 2 times n2 of t. Lambda 2 is a constant, so we can bring that outside the derivative operator. And so this just equals lambda 2 times dn2 dt. And since that equals 0, then we can just cancel out that lambda 2. So really we just need to find, and it's not surprising that whatever time gives us a maximum for the inventory of isotope 2 is the same time where the activity of isotope number 2 is at its greatest. So recall from the balance expressions, because this is what we started with when we derived all this, that this is just going to be lambda 1 n1. We're receiving that from isotope number 1, and then decaying down to isotope number 2, we're losing this. This is our sink, lambda 2 times N2 of T. And we want that to be equal to 0. And we have expressions for N1 and N2 that we developed from the notes. If we take those and plug those in, then we just want to see where these first two terms here become equal. And so this just becomes N1 naught lambda 1 exponential minus lambda 1t. And we want to see where that equals lambda 2. I also had a initial inventory there. This would be lambda 2 minus lambda 1. And then I had 2 exponentials here. So these two terms all cancel out, and if I divide through by that exponential and move the lambdas to the other side, I'm left with the following: lambda 2 minus lambda 1 divided by lambda 2. This is going to equal 1 minus the exponential of lambda 2 minus, or lambda 1 minus lambda 2. T. Now I can just solve this for the time by taking the natural log of both sides and manipulating it, and I will find out that once I do that, then this T max is going to be equal to the natural log of lambda 1 over lambda 2 divided by lambda 1 minus lambda 2. And with these lambdas, I get my lambdas from these here. So lambda is going to be equal to the natural log of 2 divided by the half-life. So I know the half-life, I can find lambdas, and once I do that, then I find out that this is going to be equal to 39.19 minutes. And we're going to substitute that back into the expression for N3. And then once we have N3, we'll convert that back to grams because that's what it's asking us for. And we find out that N3 of T max is going to equal 3.297 times 10 to the 14th atoms. And for this isotope, uranium-233, then this is going to be equal to 0.1276 micrograms. We started out with 0.5 micrograms of nothing but plutonium-233, and by the time we reach almost 40 minutes, then a portion of that, 25%-ish, has converted to uranium-233. So let's look at this in MATLAB. We can take the same approach here, but I wanted to share another approach to this. Now I'm using MATLAB, which has built-in functions for what I'm about to do, but there are going to be similar tools available to you regardless of the programming language that you decide to choose. And so at the beginning of all this, we started out with a set of differential equations. And all I need to do is solve those differential equations. And so I can do those numerically. And the benefit of doing it in this fashion, there's a drawback, I'll tell you about that in a minute, but the benefit of doing it this way is that you can specify whatever initial conditions you want. It doesn't have to be, you don't have to be restricted to the scenarios that we've been restricting ourselves to in the notes and in the sample problems, where all the inventory is of isotope 1 in the beginning and there's nothing of anything else at time equals 0. But this one we can start with whatever ratio of inventories we want. We can have only a small portion be equal to the original parent. And so what are we doing here? We're marching through just like we did on paper. We've got Avogadro's number. We know the mass. This is the initial mass of isotope 1. We got a half of a microgram, so 0.5 e to the minus 6. And I have this AMU lookup function, so plutonium 233 is going to have protons 94 and nucleons 233. And so because I know that, I can find out the number of atoms for isotope number 1. And I'm going to use that in my initial condition. In this case, I'm going to use a vector. And it's 3 elements long because I have 3 isotopes that are part of this chain. And the half-life, I only have 2 half-lives because I'm considering that final isotope to be stable. And we looked those up already, 20.9 and 36.2, that was in units of minutes, and so I'm going to convert that to seconds by multiplying it by 60. And then once with knowledge of the half-lives, I can easily just calculate my decay constants, lambdas. And just as a reminder, in case anyone's wondering, the log in MATLAB programming environment is the natural log. You have to use log base 10, log 10 to get what I think in many cases would be represented by just log. So a natural log of 2 divided by the half-life. That's going to give me my lambdas. And I calculate the time for A2 to reach a peak. And this is what the expression is that we would have found going through the analytical. And then this is where we can make use of built-in functions in MATLAB. And so I want to go from, see, it was 30, and so let's go like 50 hours. So 50 hours or 50 minutes. Let's go 100 minutes. 100 minutes times 60, that converts it down to seconds. So this on line 12 is going to give us the span of time over which to run this numerical integration of these sets of differential equations. Start at time equals 0 and go up to 6,000 seconds. And this is the function built in. This is ODE45. And if we type in the help menu here, we can see that this will solve a set of differential equations, and the inputs to those are going to be the actual function that we're evaluating. More on that in just a minute. The span of the time and the initial values, the initial field for each of those. In this case, we have N1, N2, and N3, and initially I've got N1 not, but I could, and 0, 0, but I could have non-zero entries in those as well. And the output to this is just going to be some time vector, and then the output y values. And so these are going to be N1, N2, and N3 as a function of time, that first vector. So let's talk more about this function then, that's right here. This first entry, in the MATLAB language, this is telling MATLAB that there's a function that is going to have variables t and n, and then I want to output t and n over here. But then I make a function called chain decay, and with it has 2 inputs. It has n and lambda. And if we go to chain decay, you can see that this is just nothing more than the set of differential equations. And so if this were, let me comment this out. If I wanted this to be only able to solve the chain, the decay chain that I was looking at here, which is 3 elements long, then what I would do is I would say, well, I still want this in there, but I'm going to initialize the fields, and then I'd say, well, no, I wouldn't need to do that. But dn dt, so that's a representative of my derivative for the first isotope is going to be equal to negative lambda, that first lambda, and so I need to input a vector of lambdas in here and a vector of n's, and I'm going to get out a vector of dn dt's. And so if I know lambda 1, which is an input, and I just multiply that by n of 1. And then I want to do the same thing for the second expression. In this one I had a source, which was lambda 1 times n1. And then I had a sink, which was lambda 2 times n2. And then for my final differential equation, I just had a source, so lambda 2 times n2. And that's really all I need for this function. And so let's go ahead and save that, and we can run this. But again, all this is doing is listing your set of differential equations. On the left-hand side, my dn dt's for 1, 2, and 3. And on the right-hand side, the sum of the sources minus those of the sink. So in my first equation, I just had a sink. In my second equation, I had a source and a sink. And in my final equation, I just had a source. So this will only work for this specific type of problem with 3 elements long and that sort of thing. So if I go back here and I call that function and I input the n and the lambda, my initial conditions are in this vector I'm calling n naught, which is up here, and I've already defined t-span, and so this then is going to numerically step through each of those differential equations and then give me results that satisfy those equations numerically. So it's not going to give me an equation out, it's just going to give me numerical values that are represented by those equations. And then I want to calculate the activity. Now that this is going to give me a matrix that is how many ever rows long that my time becomes, which that's something that the function just is going to choose on its own. But I have this, then my second output is going to be that many elements in the rows, and then in this case is going to be 3 columns because I have 3 different n values, n1, n2, and n3. And for each one of those, I can find for my first 2 at least, I can find the activity. And then once I have the activity and the number of atoms, then I can just evaluate that for isotope number 3 all the way at the end of the time vector. And so we'll end up coming back up here and change this from 100 minutes down to this t peak, whatever that ends up being. And that then will allow me to use this to find the total number of atoms at the end of the simulation. And then by knowing the fact that this is now uranium, so 92 protons, 233 nucleons, U-233, and again the total number of atoms and Avogadro's number. and then plot the results. So let's look at this. And this error here is because I am not forcing this to be a column vector. And so I need to uncomment that line. And I think that should do it. So we've got figure 1 is our activity in Curies, and this is the inventory for that, and you can see that this is about 39 or 40 minutes where I start to see the peak in the inventory for isotope 2, and it's the same location where I see the peak in activity for isotope number 2. And if I want to come back now, well, let's finish the problem first, and then we'll redo it with a more robust chain decay function. But I want to find this location for the peak activity of that second isotope, and I did that analytically here. And so all I need to do is change the time span going from 0 to 6,000 seconds to this value of t peak, whatever it ends up being. And we can see that t peak is calculated as a little over 2,300 seconds, 2,351 seconds. So I use that as the final time that I want to simulate to now, and I go through this differential equation system of differential equation solver and run through the whole thing, and whatever I get here for this mass is what the answer will be. And when I ran it for 6,000 seconds, then that mass ends up being 0.35 micrograms. But if I change that time now, I'm expecting that number to go down. And so now I'm only going to 39-ish minutes, and that's where I reached the peak. And we can see that the mass there is going to be 0.127. 0.127 micrograms. So if we go back now to the chain decay function, I can delete these lines and uncomment now all the rest of these. So what this is doing is it's making it more robust. I am dealing in this specific example with a decay chain that is 3 elements long, 3 isotopes long, but maybe I have one that's 5 or 11, and I want to be able to use this same function because the form of the equations are going to look the same. If I'm just talking about decay, going from one isotope to the next, to the next, to the next until I get to a stable isotope, then I want to be able to simulate all those decay processes. And those equations all look the same. If it's the first equation, that's what these lines are doing here, then I only have a sink, and that's what this is. If it's the last equation, then I only have a source. So that's why I got a negative here and a positive there. Everything in between, that's what these lines are, is going to have both a source and a sink. And whatever, as I step through in this variable I, then I look at the previous parent, so my immediate parent, find its lambda value, find its value for n. That's going to be my source, and then the sink is going to be my value for lambda and my value for n. And so this now I can explore scenarios of as many decay processes as I want to. Okay, so let's go back to the notes now, and we're going to consider simple decay chains now of arbitrary length. We've looked at decay chains of 3 isotopes long, but in reality this could be a decay chain of any number of isotopes. So we're going to look at some arbitrary length, and the equation that I'm going to go over to make sure you know how to use it, and then we'll code it up in MATLAB. This is in the textbook, but it can be a little confusing on how to actually implement it, and so I want to make sure that you're clear on that. But one thing to be mindful of is that this is the assumption that this expression is going to be rooted in. In other words, the initial sample has 100% of its atoms being that of isotope number 1, of the initial parent. And so what this looks like is we have X1 decaying to X2, which then decays with decay constant of lambda 1 and then lambda 2 to X3. And that'll decay with lambda 3 decay constant. And then we'll have some xj, that's the more generic term here, which will come from a lambda j minus 1 decay constant, and then have a decay constant of lambda j. And eventually we'll have some stable isotope xn, which has a decay constant preceding it of lambda n minus 1. And so this is the scenario that we're talking about in arbitrary length. And what this means here, that statement there, mathematically means that the inventory, because I have j or n isotopes, for j equal to 1, that's going to be my initial isotope number 1. That's going to have some atom count to it, and the rest of these, where j is greater than 1, all of those are going to be 0. And so the expression that we have for the activity then of the jth isotope as a function of time is going to be that initial inventory of isotope 1, and then we're just going to have a bunch of terms that we sum together. And this will be Ci times the exponential of lambda I times t. And so this looks like the following, and then we're going to multiply this by C1 times the exponential of negative lambda 1t plus C2 exponential of negative lambda 2t, and so on and so forth until we get to Cj, negative lambda j_t. And these C's here, we have the, presumably we know, or we can at least look up the decay constants for each of the isotopes, lambda 1 through lambda j, all the way to lambda n minus 1. But these C's then are the only unknowns, and the way that we would use those for this mathematically, for this problem as it's defined mathematically, is this here. This is my C m value. And so if this is my product term here, so this numerator then is going to be lambda 1, lambda 2, lambda 3. I'm multiplying them together all the way to lambda j. And in the denominator here, I'm going to take each of these lambdas and subtract them from whatever the C subscript 1, 2, or 3, whatever it is I'm looking for, that's the lambda I'm going to subtract from all the lambdas available to me. And so this would look like the following: lambda 1 minus lambda m, lambda 2 minus lambda m, and then we multiply these by lambda j minus lambda m. And what we're going to do is we're going to exclude this difference when I is equal to m. In other words, there's not going to be any term here where we have lambda 2 minus lambda 2, because that's 0. That's going to blow up the expression for Cm. Okay, so to demonstrate this, let's look at the case below. Here, this is the case we just did a minute ago. We found the analytical solution to it. So let's just double check and use these expressions to make sure we get the same answer as we did before. So we've got x1 to x2 to x3. And so the activity of 1 is going to be, according to my expression, n1 of 0 multiplied by how many ever terms I have. Well, I'm looking at the first isotope, so I only have one term. I have a C1 and a lambda 1, and that's it. And so this would be n1 naught times C1 times the exponential of negative lambda 1t, where C1 in this case, since I'm only going to isotope number 1, my numerator here is just going to be lambda 1. Right, this numerator here is just going to be lambda 1. And then the denominator is going to be it's going to be only one long, so it would be lambda 1 minus lambda 1, which we're going to ignore that, so this will just be divided by 1. And so this is lambda 1, and so my activity, the activity for isotope number 1 is the following expression, and this is, hopefully we recognize this, we've done this enough times to know that that is the exact expression that we would expect for the activity of isotope 1. Now for the activity of 2 is the only other one that we need to calculate here, because there is no activity at 3, that's our stable isotope. So this will be my initial inventory times C1 times exponential of lambda 1t plus C2 times the exponential of negative lambda 2. So that's my expression. Now I just got to find C1 and C2. So C1, what does it look like? My numerator is just going to be the product of all the lambdas. So that will be lambda 1, lambda 2. And the numerator for C2 is going to be the exact same thing. And if I had 5 terms, then that numerator would be lambda 1 times lambda 2, lambda 3, lambda 4, lambda 5, and it would be the same numerator for all my C values, C1 through C5. The denominator is what changes. And so I have 2 terms in the denominator that I'm going to be looking at. I would have lambda 1 minus lambda 1, which would be 0, but again I'm ignoring that, so I replace that with just a value of 1. That's representing my lambda 1 minus lambda 1. And then I have lambda 2 minus lambda 1. And for the C2 then I have lambda 1, my m in this case, my Cm is, the m is 2, so it would be lambda 1 minus lambda 2 multiplied by lambda 2 minus lambda 2, which again we replace with a 1. And so you can see how, if I compare C1 to C2, 1 is just, the only thing that's different is the denominator, the lambda 1 and lambda 2 switch places, so it's 1 is just the negative of the other. And that's exactly what we expect it to be if we go back and look at our notes of the analytical derivation of this. And so A2 ends up being in my initial inventory. C1 is going to be lambda 1, lambda 2 over lambda 2 minus lambda 1, plus C2, which will be lambda 1, lambda 2 over lambda 1 minus lambda 2. And so I can take these now and I can combine them just by letting 1 be equal to just by swapping the denominator order and then bringing a negative out in front. So A2 T is going to be equal to that initial inventory multiplied by that lambda 1, lambda 2 over lambda 2 minus lambda 1. And then I get the minus term here because that coefficient, I changed the order to be lambda 2 minus lambda 1. And this is, you can go back to your notes and check this, but this is also good. And so the same principles apply for when you're creating these coefficients, the CMs, for any number of length decay chain that you might have. So let's look at this in example 12.3. In 12.3, we want to recompute the what we did in example 2, but we want to use this analytical solution that we just went over for simple decay chains of arbitrary length and verify that the results are unchanged. And so this again was a 3, although the U233 wasn't fully stable, we considered it to be stable given the time length of interest, time window of interest to us. And so this is a 3 element long decay chain. And so we'll go to MATLAB and look at this and develop some code for the expressions we just found. So in this case, we are going to do all the calculations like we did before. Here's my ODE 4.5. So this is the same numerical solving of the expressions that we were doing in example 12.2. And then we calculate the activity from there. But we want to do this in a second way. So we're going to go through all that time vector, and we have 2 different activities that we're trying to calculate. So I'm going to call this A new, and I'm going to compare that to A. So I'm plotting just like I did before. I have the activity here, and I'm dividing by 3.7 e to the 10th. So now that's going to be in units of Curie. And I'm going to do the same thing down on figure 3, but I'm going to take A new, which is calculated from this function, chain decay activity. And so if I come here to chain decay activity, then this is what's calculating those coefficients and then adding them all together to get the activity at the end of it all. And so the inputs to this are my initial inventory for isotope 1, the lambda, which is going to be a vector, meaning if I have 3 elements, then lambda needs to be 2 elements long, because I've got the decay from 1 to 2 and the decay from 2 to 3. And then whatever time I'm looking at. And so I can just call this function each time and evaluate different times in order to create that plot. And so my first task is to get that numerator. And as I mentioned before, that numerator is going to be the same for each and every coefficient C1 through whatever, how many ever C's you have. And it's just going to be the product of all of the vector of lambdas. So if I have 2, it's going to be the product of those 2. And then we allocate space for the denominator, and you see that it's a simple ratio of those 2. We take the numerator divided by the denominator, that gives us our C. And so this is just allocating space here. But here's where I'm going to cycle through each of those lambdas. So I've got 2 in this case, and so I'll go from 1 to 2. In the first one, I'm going to take lambda. I'm going to call this lambda new. Maybe we should call this lambda difference, because that's what we're doing. We're taking the lambda vector and we're subtracting one value of lambda. And when I equals 1, we're taking the first lambda, so lambda 1. We're taking the entire vector. If it's 10 elements long, we're subtracting lambda 1 from that, so that my first element now becomes 0 and the rest of them become non-zero. And so all I'm doing here is just saying, give me now the product of this lambda new, which again we could just call lambda difference. But I want to say, I want to evaluate, I want to take the product of everything in there that is greater than, whose absolute value is greater than 0. So this little input here gives me an index call out where I get everything. I take the absolute, because sometimes that difference will be a negative number, sometimes it will be a positive number. And so I want to take the absolute value of that, and whenever that number is not 0, I want to account for that in my denominator. The one that is 0, there should only be one that's 0, I want to leave that out. And so this highlighted region here is just going to give me an index array to say, don't take this one and take the rest of them. And so I use that as the input to this vector, lambda nu, which was the difference. And so then it just collects everything from that vector that is non-zero, basically. And whatever that new vector is, it's going to be one element less than the original lambda vector was, because one of those was 0 and I kicked it out. And I just want to take the product of all of those. And that's going to be the denominator. And then I do that. I just take the ratio of the numerator to the denominator, and that's my CM value. And the subcomponent of the A, then, the activity due to isotope I, so in 1 or 2 or 3 or 4, is just going to be that Cm of that same index I times the exponential of minus lambda and lambda of I times t. And so this line here, line 16, is giving me the activity due to that specific decay of that specific isotope, isotope I in this case. And then I'll cycle through those. And so I'll have this value will be, if I just have one time that I'm evaluating this, then that's going to be 2 elements long if lambda is 2 elements long. And then all I do to get the final activity is just sum all of those up and then multiply all of that. That was my summation out in front. And I multiply that by my initial inventory, just like the expression gives. And that's the activity, and that is what I use as the output to this. And so coming here, I can just call that chain decay activity, and the inputs to that are going to be my initial inventory, and we'll talk about this line here, but that's basically my lambdas. And then I'm cycling through this time vector, and so I'm gonna call this every time I'm evaluating a new time. Now this lambda, I can't, because when I'm stepping through them, I shouldn't evaluate the entire chain of lambda. I need to look at a sub portion of that. And so what this line here is doing, line 41, is saying from the lambda vector, only take the first I number of elements. And so if I equals 1, I'm looking at that first decay, and I only want to use that first lambda. As you recall from the notes, that C1 only had lambda 1. And then I call this function here and then get my activity. And then this creates a matrix basically that's J rows, which is according to the time, and I columns, which is according to how many different values of lambda that I have, how many decay processes I have. So I run this, and I just want to compare figure 3 to, that's my count. So it's really figure 1 and figure 3 that I want to compare. And so we can see that these two are identical. And so whether I numerically integrate, and we already have proven the fact that the numerical integration gives us what the analytical solution gives us, or this figure 3, which is sort of the shortcut to the analytical solution. But the benefit with this now, this function, is I can use this for as many isotopes as I have in that decay chain. So that is a bit of code that shows you how to implement that shortcut to the analytical solution with the CMs and just sum up all those subcomponents to get your total activity for the jth component. Okay, so let's go back to our notes, and we'll look at this in a little bit more comprehensive fashion, where we have what's called an open system. In an open system, then we have for each isotope, there's an option or possibilities for this isotope to appear through avenues that are not related to decay at all. And so the most classic one that we'll consider in depth in the next chapter, in the next module, is through fission. And so I have fission products. And every time this uranium-235 nucleus splits, I can't possibly predict exactly what's going to happen, but I statistically know the likelihood of this happening or that happening, of these two daughter products and one neutron, or two stray neutrons, or sometimes three stray neutrons. But at any rate, that P term here, this production term, is what is accounting for that fission. And so I could be getting this from fission or some other source, but that's the main one we're going to consider. And so my sinks here, this is the losses, and the sources are going to be the production terms, these cursive L's and cursive P's. So this is my production, and this is my loss. And so if I take any one of these isotopes, I've got the initial isotope X1, and that we still got the decay chain going along. We got lambda 1, lambda 2, lambda 3, all the way to some stable daughter at the end of that decay chain. But all along the way, I can be adding to each isotope through the production term, but I also can be losing each isotope externally through this loss term. And so if I didn't have any production or any loss terms, then I have the same thing that I've been investigating so far in this lecture. And that's a closed system. But in this case, I've got an open system. So let's take this generic kind of internal analysis and look at what my rate of change balance will look like. I've got dN dt, so ddt, the time rate of change of that isotope, the number of atoms, the number of nuclei, that's going to equal the sum. Remember, the things coming into that isotope are going to be positive terms. Those are my production terms, and the things leaving that are going to be negative terms. And so I've got some production term, some generic production term, some external production term. Plus I have the lambda of the parent directly preceding this isotope. And then I've got losses. So I've got my external loss. And then I also can be decaying down to the next daughter. And so this will be lambda j and j of t. And so this looks identical to what we just had, with the exception of these one extra production term and one extra loss term. And so this is the expression I would have for every one of these isotopes except for the first one and the last one. So all the internal, if you will, internal isotopes in this decay chain, they're going to look exactly like this expression here, just with different values of j. J2 through j equals 2 through j equals n minus 1. And so for the first one and the last one, I just need to treat these differently. So for j equals 1, then I just have dn1 of t dt. I have the production of isotope 1, and I have the loss term of isotope 1. I don't have a decay from its immediate parent because it has no immediate parent in this diagram. But I do have the option to decay away. So this will be lambda 1 and 1 of t. So that's what my differential equation looks like for j equals 1. And then for j equals n, which is my stable isotope, then I've got the n of t dt. I have a production term there. I have a loss term there. But actually I should put them together to be consistent. So I have a production term, but I also have the decay from the immediate parent, so n minus 1 and minus 1 of t. And then I have my external loss term. And so I've got one equation here. I've got one equation here for the first term and the last term in there, and then I have n minus 2 equations here. And so I add all those, accommodate for all those. I've got n equations, I've got n differential equations, and I just need to have n number of initial conditions. So the initial inventory for each isotope. And so the solution to this looks like the following. And we arrive at this just the same way that we did for a more simplified case. We apply an integration factor and combine terms here, combine terms there, and we're going to, initially this was my integration factor, and then we're going to need to integrate this expression here. And so I need to know what that production looks like. I need to know what that loss looks like. And in some cases I can neglect one or neglect the other, or if I neglect both, then I'm going to be left with the exact same expression that I had before we even started considering this as an open system. And so this then is the expression for the inventory of isotope J. So this will be in J at t equals 0. And I just need to know what my production terms look like and my loss terms look like. And the rest of that is the same stuff we've been doing this whole time. But again, note that if P of my production of isotope J and my loss term of isotope J, if those are 0, then we once again have a closed system. Okay, let's go to our final example. In this case, we want to consider the following open system. We have production terms for 1, 2, and 3 are represented down here in part B, but part A is just to set up those differential equations, those differential decay equations that we just were focusing on, and we supply the equation here that we were just looking at just a minute ago. So part A is to set up those differential decay equations. Part B then is to consider specific expressions for P1, P2, and in this case we're not given P3 because we're only asked to find expressions for N1 and N2, but the process will be the same. We could go all the way to N3 and N4 for that matter. Okay, but let's see. So initially, and notice in part B, this is different than what we've done in the past. Initially, so in the past, what we've had is the initial inventory is 100% isotope 1, and then that decays to isotope 2 and 3, and then becomes the stable isotope 4 in this case. But for this particular problem, we are saying that initially we don't have any of those isotopes. And so initially, that inventory is all 0. We have atoms maybe of something else, but we don't have any of isotope 1, 2, 3, or 4. But we're getting them from the production, and from isotope 1, not only is it production, but then it feeds through decay to isotope 2. So with isotope 2, you've got the decay from isotope 1 plus the production term coming in. And in this case, there's no expressions given for the loss, and so we can go ahead and neglect this for all of the terms there. And because of this here, my initial inventory is going to be 0, so I can get rid of that term. And so what does this look like for part A? I'm just setting up the differential equations again, and this would look like I have the exponential, the differential equations would look like the following. So dn1 of t dt, what are my production terms? What is the stuff coming in for isotope 1? I just have P1 of t. And I don't have any decay coming into isotope 1. And so that's all my positive terms. What are my negative terms? Well, there's no losses, as we already have discussed, but I do have decay. So decay down to isotope 2 will be this expression there. So that is my differential equation for isotope 1. For isotope 2, I do the same thing. And I've got my production, and then I've got isotope 1 coming into isotope 2. Everything that decays from isotope 1 becomes isotope 2. And then going out, I've got the following. So I decay down to isotope 3. And my differential equation for N3 is going to be my production term plus the decay from its parent, which was lambda 2 N2, and then its own decay down to isotope 4. And my last differential equation, I'll have some production for isotope 4. Actually, no, we don't. We don't, because this here tells me that I have production terms for 1, 2, and 3, but none for isotope 4. And so this actually becomes even simpler. The only thing coming into isotope 4 is going to be through the decay from isotope 3. And so that's going to be a positive term of lambda 3 N3. And so this is the answer to part A. When it says set up the differential decay equations, this is what you would do. And so I could solve these analytically. In part B, I'm given expressions for P1, P2, and P3. Well, P1 and P2, because I'm only asked to solve these two for part B. But I have production terms 1 and 2, and so I could solve all these analytically and apply an integration factor just like we talked about. But this is my integration factor, and what would end up happening is I would be left with the exact same process as is described in this main equation here. And so all we need to do for part B is just apply that equation. So for N1, then I got my first term dropping out because my initial inventory is going to be 0, and so all I'm left with is the rest of this, which is going to be exponential of minus lambda 1t, and then I've got to do the integral from 0 to t. I've got my production term. I don't have anything decaying down, and I don't have a loss, and so it's just the production term here. So this would be P1 of t times the exponential, that's my integration factor, of lambda 1 t, and I just need to integrate that. And for this particular problem, as we go back up to the problem statement, then P1, the production term for isotope 1, is just a constant. And so because that's a constant, then I can bring that outside the integral. And once I do that, then I find N1 of t equals exponential minus lambda 1t times B1 naught. And then I integrate the remaining exponential term, and that just becomes 1 over lambda 1 times the exponential of lambda 1 t, and then I evaluate that from 0 to t. And so once I do this, I've got P1 over lambda times the exponential of lambda 1t times exponential of lambda 1t. That's evaluated at the upper bound here. And now when I evaluate that at the lower bound to 0, I get minus 1. And so N1 of t is going to be P1 naught. If I multiply this through, then I will get 1 minus the exponential of negative lambda 1 times t. And so what does this look like? If I got a constant production term, then at time equals 0, I've got an initial inventory of 0. That was the initial condition that we knew we had. And as time goes to infinity, then I have some constant value of inventory, and that value is going to be equal to the production term divided by lambda 1. This should all be lambda 1. So that's my expression for n1. And we'll do the same thing now for n2. N2 of t. That first term again drops out because I don't have any initial inventory of isotope 2, so this will be exponential of lambda 2t. And then I've got this integral from 0 to t of p2 of t. And then I've got my additional term in there, this lambda from the preceding parent. And so this then is minus, plus lambda 1 n1 of t. And I'll multiply that by that integration factor. This should have been negative, sorry. And then I have to integrate that. And so the expression for P2 from the problem statement was P1 naught times exponential of minus lambda naught t. So that's what I would evaluate for, or what I would put in for P2. And we can carry this integration out. So it's going to be a little more complicated than isotope number 1, but again, it's just keeping track of our integration and then knowing what to do with that integration factor and evaluating it at the bounds, that sort of thing. But what I'm left with at the end, you can do this and check your work. For this scenario, and notice that lambda naught has nothing to do with any isotope. It just happens to be some decay constant or some exponential constant that relates the production term for that isotope number 2. Exponential of minus lambda naught t minus the exponential of minus lambda 2t plus 1 over lambda 2. There's 1 minus exponential of minus lambda 2t, or minus 1 lambda 2 minus lambda 1 times exponential minus lambda 1t minus exponential of minus lambda 2. And so this is the solution for the inventory of isotope number 2. And if we want to find the activity, then we just multiply each one of these by their respective lambdas. So the top expression we multiply by lambda 1, and we see that the activity itself is going to reach some saturation value that is equal to the production term. And then likewise we could just multiply this bottom expression by lambda 2 to get the activity of isotope number 2. And so we can do this for any and all isotopes where we have the expressions for production. And this could be a step function, it could be a sine function, it could be a ramp function, it could be a quadratic. I mean, it could, as long as you have a functional representation of that production term, you can perform this integration. All right, well, that concludes this lecture. We'll see you again for lecture 13.